Welcome in. All right, so introduction to waves. This is a little quiz or a test, whatever you may want to call it. So there's a good set of questions, both multiple choice and some calculation questions. I'll put up this exact copy, so PDF copy, in the description. You can download it, try it out for yourself, and then come back for the solutions in here. All right, so let's give it a go. Okay, so the first thing is, I guess we're going to be rounding to 3 significant digits when we have to, and providing answers in SI units. Okay, so I'll do that, I guess, for future questions. Now, for these ones, the multiple choice ones, okay, let's take a look at these. Okay, so first one, mechanical waves. All right, so mechanical waves, let's see. So carry energy via particles in a medium. All right, so, well, that sounds definitely pretty good. Carry energy via electromagnetic, no, so definitely not. Electromagnetic fields do not carry energy. Well, they definitely do carry energy. Are always passed through elastic medium, no. All right, so the answer is A. Okay, so that will be the first one. Okay, so let's take a look at 2, vibrations. So vibrations are linear motions away from an equilibrium point. So linear, well, definitely not necessarily linear. Our B is our cyclical motions away from an equilibrium point. Okay, so they're definitely cyclical, so vibrations go up and down, but they go around the equilibrium point. So it's not going to be B. Our cyclical motions about an equilibrium point. All right, so that one looks pretty good. Okay, so this one is going to be C right here. That's for question number 2. So this is related to vibrations. Question number 3 there on multiple choice. So a transverse wave. So remember, transverse waves, so the particles are moving perpendicular to the actual motion of the movement of the energy of the wave, right? So they're going, let's say, up and down, and then the wave carries over in this direction. So they're unlike longitudinal waves. So let's see what they have in here. So a transverse wave involves the vibrations of particles parallel. No, not parallel as the direction of energy flow. So definitely not that. So we're looking for perpendicular. So that looks B. Involves the vibrations of particles perpendicular to the direction of energy flow. All right, so this is going to be B right here. So this definitely looks pretty good. Okay, now the other ones involve vibrations of particles. So linear to the direction. No, so not necessarily linear. Non-linear. Okay, so definitely those not. Okay, so parallel or perpendicular, those are the 2 you're looking for in terms of wording, but parallel would be a longitudinal wave. So a transverse is perpendicular. Now, for question number 4 there, so a longitudinal wave or waves are comprised of only compressions, no. Okay, it says compressions and rarefactions. Only, so not B either, only of sound of waves. Well, no, the sound of waves are longitudinal waves, but they're not the only example of longitudinal waves. Have both compressions and rarefactions, so that is true. So this is going to be D right there. All right, let's carry forward. Wavelength is best captured by, so wavelength, so recall that wavelength is the total distance, okay, that we have for one full complete cycle of a wave. So total energy, so no, it has not measure energy, the total distance for one cycle of a wave. Okay, so there you go. So this looks like it's going to be B. So it has nothing to do with period of time. So wavelength does not capture time. So that would have been period and frequency. The distance between a crest and a trough, no. Okay, so not necessarily crest and troughs there. So B is the right choice. Question number 6. Amplitude of a wave. So amplitude, okay, of a wave, so as you're going through, is the distance between the crest and the trough. No, it is not. So it's not from kind of peak to bottom or bottom to peak. So that's not true. Is positive for the crest and negative for the trough. No, it's amplitude is always positive, actually. Is equivalent to the phase shift. So no, it's nothing to do with phase shift. Aligns with the wavelength. So no, okay, so amplitude does not align with the wavelength. It's not the distance. So it looks like really the best choice here is going to be none of the above. All right. And amplitude, we're going to get into amplitude in just a moment because here's going to be a nice example for us. So here's another question. So question number 7. So here they're asking us, for the red wave, find the wavelength. All right, so that's one thing that we want to be able to find. So find the wavelength. This is for the red wave right here. So that's going to be this wave that is carried through. Just going to highlight it for us, just so that we can have it right there. That's what we have. Find the amplitude. All right, so that's going to go back to the previous one. We're going to be able to find the amplitude shortly. And then find the phase shift of the wave with respect to the blue wave. All right, so we also have a blue wave there, as you can see there. And we're going to try to find what the phase shift is. We're going to do the proportional, and this is a pretty good exercise because it reminds you of what the phase shift is for the wave in general. All right, so for the wavelength, what I like to do is, make your life as simple as possible. So you want to be able to find kind of two points which are exactly at the same kind of phase shift that you have in there, or the exact phase that you have within the wave. And this is going to be, so this is going to be from here to here. Notice that it is distance, okay, that we're measuring, and that's indeed what this would be. So this full out distance, so this is one complete cycle of the wave. Now, do you have to pick between these 2 points? No, you can pick at whatever convenient points that you want. We could have, for instance, picked from all the way from here to all the way from here, but it looks like this would have been very difficult for me to read this out. Now, the reason why I chose this point right here and this point right here is because when I go down here, notice that it nicely is stuck at 2 and this is stuck at 8. So I can find the actual wavelength. So the wavelength within here is going to be equal to just 8 minus 2, which is the difference. So it's going to be 6 meters. So this wave is 6 meters, or at least it has a wavelength of 6 meters. So that would have been the first thing. All right, so that's 6 meters right there. The amplitude that we would have, now we have to be careful with amplitude. So as you're going to be measuring this out, so the amplitude is always the distance from the equilibrium point to the peak point, or from the equilibrium point to the trough, right? So to the bottom point. However, it's the positive value out of that. So I have to find the equilibrium point. Now notice the equilibrium point is definitely not, okay, our kind of axis line, which is this line. Now it would be for this blue line, so that is indeed the equilibrium point right here. And this would have been the actual amplitude of the blue line right there. So the blue line, as you can see there, it would have been amplitude of 1 meter in terms of height. Now, because this one looks like it's been kind of shifted upwards, the equilibrium point, I'm going to kind of draw this out in here. It's going to be the middle point, right? So if I would draw a line, so the middle point is going to be at 1. Okay, so I'm going to draw this out. So this kind of almost got shifted right there. So this is my line. Let me make it straight here. And now the amplitude is basically nothing else but the height, okay, that you have. Okay, so either in this direction or, all the way to the bottom, but you're going to take the positive value out of that. So as you can see there within here, so if you take this, you can certainly zoom in there. It looks like it's 4 meters, right? That's what we have there. But the equilibrium point right there, so be careful because this is 4 meters, equilibrium is at 1 meter. So that means this distance is 4 minus 1. So that means my amplitude will be 3 meters. All right. Or you can go from 1 all the way to minus 2 in here. And again, that simply is 3 meters. So that's my amplitude. That would have been the second piece that we had to find. So wavelength 6 meters, amplitude 3 meters for this one. And the phase shift, now this one is probably the trickiest one of them all, is something that we have to be able to find, and it's always relative to something else. Now they're telling us with respect to the blue wave. So what we have to do in this situation, I'm going to try to erase all of this stuff in here just so that it's kind of out of the way for us, and then I can concentrate on the phase shift. So the phase shift is going to be something of this nature. So what we have is we want to be able to find if this wave has been shifted with respect to another wave. So what you can do is the following. You can find, so what I like with respect to the blue one, because it's nicely captured here at 0, right there, notice that there's a peak there, and then here you have another peak, and then here you have another peak, and these peaks continue on. This actually is one full cycle, okay, of the wave, so it goes from peak to peak. Now notice that the red wave, obviously, so all the way, it doesn't start here, right? It doesn't go like this, okay, and then continues on. It's been shifted over. Now notice where its peak is. So here it looks like the peak has been shifted. The phase is 2, okay? So this is the actual phase which aligns, which is the position of the peak relative to this. This is basically shifted by 2. Okay, so that's the position. Now, if you want the actual phase shift overall, it's going to be shifted. Okay, so how much did it get shifted with respect to the entire cycle? So we said that the entire cycle, so the wavelength was 6 meters. That was the entire cycle that we had. We're noticing that this position has been shifted over, so in this direction, by 2, right? So that's the phase of 2. So now that means the phase shift, which often sometimes is given like this, okay, that you have in here. Now, this proportionally will be, so with respect to the entire wavelength, okay, which is 6 meters, it's been shifted 2 meters. So 2 out of 6, so 2 meters over 6 meters. So this is going to have a phase shift of 1/3. So it's got shifted a third of the entire cycle. That's what you would have in there. All right, now the last component of this question asks us, based on the given information, can you provide frequency and period of the waveform? The answer is no, not from this, because we only have the distance of the wave, so it's basically just traveling along, and we can see that the actual height that we have in here, so how these maybe particles are moving up and down in here in terms of the wave, but we have no information of time, so we cannot mention anything about frequency or period. So that is it, okay, for this example. Here's the other example. So we have a longitudinal wave, and this wave has been generated by a medical device, and it moves, okay, at a speed of 350 meters per second. So we have the speed, so 350 meters per second. If the frequency, so if the frequency is, looks like 25,000 hertz, okay, so this is definitely beyond sound. So sound is kind of up to 20,000 or so. Then what is the wavelength of the wave? Well, so this one isn't very difficult. So we can kind of go back to the speed of a wave, which is equal to wavelength divided by period, okay, or simply wavelength times frequency, right, which is kind of the universal speed, okay, or universal equation for speed for a wave. So we have speed, which is 350. This is meters per second, so this is in standard units, so that's great. Equals, now we want to find what the wavelength is, so we don't have that, but we do have the frequency, so 25000 times the wavelength, and this is going to be wavelength divided by 350 all over frequency, which is 25000. All right, so there you go. We have that. You can take out our calculator. So 350 divided by 25000, and there we have it. So this is going to be 0.014. I think they said 3 significant figures, so I'll add another 0. And this is going to be meters. So that's all that you would have for this example. Okay, so that's pretty much it for this one. Here's the next example. So we have tension in a uniform string has been set to, so we have some tension in here. So the tension is 1400 newtons. If it has been observed that a wave propagates in the string at a speed of, So this is the speed. Now I'm going to bring this back because I'm noticing this is centimeters per second. So I'm going to just bring it back to, so I guess this is 120 meters per second. So if you want to change it back from centimeters to meters, so move it 2 decimal places over for that prefix. Then what mass? So we want to be able to find out what the mass is for a string of length. So this is the length of the string, which is 165 centimeters. So again, I'll put this back into meters, so 1.65 meters. Now everything is in SI units. So, okay, now we want to be able to find what the mass is. Now, the information that has been given to us, well, mass and length are related by the linear density. So if you recall, linear density is mass over the length. Now, I have the length. I'm trying to find the mass, and I'm going to need what this linear density will be. Now, linear density I'm going to be able to obtain because if you recall, so the speed in a uniform string is just equal to the square root of whatever the force of tension is divided by the actual linear mass density. So I have V and I have Ft, so I can certainly solve for that linear density. So let me do that. So substituting this in, this is going to be 120. Now that square root, I'm going to get rid of it by squaring both sides. So this is going to be squared equals, this is going to be Ft, my apologies, we have Ft. So Ft is 1400 divided by, and then this is going to be mu. So now rearranging this equation, this is going to be mu equals 2, so 14 divided by, and 120 squared. So let's see what this gives us. So we have 1400 divided by 120 squared. So it's a very small number, 0.0972, etc. Everything was in metric standard units, so that means this is going to be kilograms per and meters right there. I'm going to leave it on my calculator so that I can find out what this mass is over here. So if I go back to this equation, so now I have this, right? So that's what you see there on my calculator. And so that's going to be 0.97, 2, etc. I have L, so now if I multiply both sides by L, so 165, that's going to give me the mass. So let me take the answer, multiply it by 1.65, and this is going to be 0.1604, etc. But this is kilograms. So if you want it in grams, which the question asks us for, and this is going to be just 160 grams. Now, if you want to put it in 3 significant figures, you will have to put it in scientific notation in here. Okay, if you want it like that. But that would have been your answer for this one. So that is it for that. Here's the next example. So this one is related to the speed of sound and how it relates back to temperature and how it's dependent on temperature. So there's 2 actual formulas. So there's a linear formula that you have, which is for part A, and then there's a nonlinear formula for part B. All right, so let's take a look. So it tells us that for a particular temperature, so here is 341, we want to be able, for a particular speed, we want to be able to find what the temperature would be right there. All right, so, well, and this isn't very difficult for us because we have to just substitute it back into the equation. So let's do that. So it's going to be 341, it's in metric standard units. So 331.4 plus 0.60696 times T. So this is just rearranging this formula. So I'm going to just rearrange it and then solve it for T. Okay, I'll be right back. So here it is, all right, and if I round this off to 3 significant figures, it's going to be approximately 15.8 degrees Celsius. So that's what we would have in here. So not bad, not very difficult for us to do. Now in part B, so if you take a look at that, it asks us exactly the same question. except it wants us to use the nonlinear formula right there. Okay, so we have to substitute for that, which is going to be 341 equals to 331.4, and then we have the square root. So it's a little bit more annoying to be able to manipulate this formula, but still very doable for us. All right, so I'm going to just manipulate this and solve for t, okay, under the square root. So let's take a look. All right, so there we have it. So notice how close these actually are. All right, so how far apart are these two calculations? Where they're 0.2 of a degree Celsius. So they're pretty good. So the linear approximation is actually really good in comparison to the nonlinear one. So very often you might run in that you will be using this one, okay, or your teachers are going to try to use this approximation. But both obviously work. The nonlinear one is a little bit better than the linear one. Now for part C in here, it says at what speed is sound traveling in air when the temperature is minus 20 degrees Celsius. Now it doesn't actually tell us which one to use, so part A or part B. So what I'm going to do is I'm going to use both of them. All right, so I'm going to take the negative 20 degrees Celsius and I'm going to substitute it into this one and into this one, and let's see what speeds we're going to get. All right, so I'll be right back. I'm going to just substitute it into the formula and find out what that answer is. All right, so we're back. They give us exactly the same thing, rounded to 3 significant figures. So you can try this out. That is it, okay, so for this example. Here's the last example on this little mini quiz for you. So it has 3 components and it deals with sound intensity and sound levels. Now, for part A, it says, if the sound intensity has been measured, 3.5 times 10 to the negative 9 watts per meter squared, so it's all in metric standard units, then what amount of power passes through an area of 15 centimeters squared? Okay, so this is an interesting question. Now for sound intensity, so if you may recall, okay, so I'll just put SI for sound intensity that you have in there, or it can be intensity just I, okay, so sometimes that's what it's related as, so you can certainly use that as well. So that is equal to power all over area. Now they give us what this is, so this is 3.5 times 10 to the negative 9. It's in metric standard units, so I'll leave it as is, at least on the left hand side. Now we want the power. Now I do have a problem because I have 15 centimeters squared, which is annoying. Meters squared, that's what you're going to have, and you can get that from your metric prefixes as well, because centimeters is just 2 away, and if you square that, so that's 4 metric standard decimal places that you would have to shift over. So if I plug this back in within here, so now it is all in metric standards, I'm going to get what power is. So power is going to be the multiplication of the two. So 3.5 multiplied by 10 to the negative 9. Okay, so that's that, and I'm going to have to take this and multiply it by 0.0015. So not a lot of power there. So 5.25, so that's 3 sig figs minus 12, and this is going to be watts. So very little power. Now remember, watts is joules per second there. But again, this is a very small little area, okay, that we have. So that's what you would have to do for part A. So for part B, okay, if you're going to be taking on that, I'm going to make this a little bit smaller. So for part B now, what is the equivalent sound level, all right, or intensity level in dB? So now we have to kind of recall, okay, so in terms of the sound level, and this is in dB, so recall that this is 10 multiplied by the log of base 10, and of course, This is whatever your intensity is. So our intensity was given to us all over the reference intensity. Now, reference intensity is basically 10 to the negative 12, right? Watts per meter squared, or 1 times 10 to the negative 12. So this is kind of the lowest level that our eardrums can pick up. And those are healthy eardrums, of course, so this just depends what you have, but this is what we've set as the level. So if I now take this and substitute it in here, so I know what this is. So this is 3.5 times 10 to the negative 9 right there. This is in the denominator 10 to the negative 12. Now this, you may have worked with scientific notation. So this actually isn't very difficult. So this is going to be 3.5 times 10 to the 3. So you can double check that. That's because they have the same base units. And of course, we have to take the log of this entire thing and then multiply it by 10. All right, so I'm going to substitute all of this in here, and let's see what we get. So we get 10 times, we need a log, and in brackets there we have 3.5 times 10 to the 3. And that's it. So this is going to be 35.4 dB. All right, so that's what you would have on the dB scale, so on the decibels scale in terms of sound level. So that is it, okay, for part B. For the last part, part C, if a sound level of 88 dB, which is actually pretty high, was measured, then what was the equivalent sound intensity? Okay, so now we kind of have to go back in reverse. Okay, so this is for the last component. So for part C, so we have 88. This is 88 dB. So I'm going to be substituting it back into this formula equals. This is going to be 10 log. We want to find what this intensity is divided by 10 to the negative 12 there. So we're basically solving this. Well, dividing both sides by 10 is easy. So that's 8.8. Okay, now we're going to have log I over 10 to the negative 12. Now, how do I get rid of that log, right? So you have to raise it to the 10. So this is working with logs and exponents. So you're going to have to take 10, okay, to the both sides. And what you're going to get is this is going to be I all over 10 to the negative 12. Okay, so that log will disappear, okay, for you. So now if you want, working with logs and going back and forth, I'll pull up a link up above there for you if you're interested or if you've forgotten. Okay, so now with this isn't now very hard. All right, so there you have it. So my intensity level is going to be 6.31. I'm rounding it to 3 significant figures, and then 1, 2, 3, negative 4. That's watts per meter squared. That would have been the intensity. All right, so that is it. Okay, so that finishes this off. Hopefully you found these examples useful, and you can let me know in the comments how many of these you actually solved. Thanks for watching. See you in future videos. Bye, everybody.